Hi, this is Kassandra explaining my PowerPoint slides explaining this project. The materials I used to create the reaction strips, it was a cardboard box, a small knife, and tape. The equations I used for D at 0 millimeters is the square root of 2 times the delta y divided by the gravity. And I converted gravity from 9.8 meters per second to 0.0098 millimeters per second. The equation for D at 5 millimeters is square root of 2 divided by the gravity times the square root of D plus the delta y minus the square root of D. The D in this case being 5 millimeters. Convert gravity from 9.8 meters per second to 0.0098 millimeters per second. The equation for D at 10 millimeters is the square root of 2 divided by the gravity times the square root of D plus the delta y minus the square root of D. The D in this case being 10 millimeters. Converted gravity from 9.8 meters per second to 0.0098 millimeters per second. The equation for D at 20 millimeters is the square root of 2 divided by the gravity times the square root of D plus the delta y minus the square root of D. And I converted gravity from 9.8 meters per second to 0.0098 millimeters per second. And the D in this case being 20. And the delta y is the standard measurement from 750 millimeters to 0 millimeters, and it corresponded with the adjacent D value next to it. And how I put it, the equation to Excel. For 0 millimeters, I did equals to the square root, abbreviated version, open parentheses, 2 times the delta y in this case being B4 divided by 0.0098. 5 millimeters is equal to square root abbreviated version 2 open parentheses 2 divided by 0.0098 close parentheses times the square root abbreviated version open parentheses 5 being 5 millimeters plus B4 in this case being delta y close parentheses minus the square root abbreviated version 5 close parentheses close parentheses. For 10 millimeters I did equals square root abbreviation version 2 divided by 0.0098 close parentheses times the square root abbreviated version open parentheses 10 in this case being 10 millimeters plus E4 which in this case is the delta y close parentheses minus square root abbreviation version 10 close parentheses close parentheses. With 20 millimeters, and it equals the square root abbreviated version, open parentheses, 2 divided by 0.0098, close parentheses, times square root abbreviated version, 20 in this case being 20 millimeters, plus E4, which in this case is the delta y, close parentheses, minus the square root abbreviated version, 20, close parentheses, close parentheses. I made this graph by inputting the D and the T into my data. The T is equal increments of 10, so each T I added 10 onto it, and I did all the way until I got 20 data from it. And for my D I did 1/2 the times the gravity times T squared. In this case G converted from 9.8 meters per second to 0.0098 millimeters per second, and I plotted D into the graph. For this one, I plugged in T and D. In this case, D was equal increments of 5 meters per second. So each D I added 5 following to it. For T is equal to the square root 2 times D, which is D in this case being this D's, divided by the gravity, which is converted from 9.8 meters per second to 0.0098 millimeter per second, and applied T in the equation, in the graph, not equation. My measured data for subject number 1 is on the left and the right, the data, and I graphed it. For subject number 1 at 0 millimeters, my mean is 283, my standard deviation is 56. For D at 5 millimeters, my mean is 257, my standard deviation is 27. For D at 10 millimeters, my mean is 249, my standard deviation is 54. For 20 millimeters, D at 20 millimeters, my mean is 212, my standard deviation is 58. For subject number 2, here is my data on my left, and I plotted the data onto my right, as you can see adjacent to it. So for D at 0 millimeters, my mean is 216, my standard deviation is 46. For D at 5 millimeters, my mean is 194, my standard deviation is 52. My D at 10 millimeters, my mean is 180, my standard deviation is 39. And for D at 20 millimeters, my mean is 178, my standard deviation is 52. For subject number 3, you can see that my data is plotted on my left, and I plotted that same data on a graph onto my right. And so for my for subject number 3, my D at 0 millimeters, my mean is 231, my standard deviation is 45. My D at 5 millimeters, my mean is 207, my standard deviation is 55. My D at 10 millimeters, my mean is 193, my standard deviation is 46. And my D at 20 millimeters, my mean is 162, and my standard deviation is 21. For subject number 4, here's my data that I plotted on my left, and on my right I plotted the data into a graph. And so for subject number 4, my D at 0 millimeters, my mean is 282, my standard deviation is 68. For D at 5 millimeters, my mean is 188, my standard deviation is 40. My D at 10 millimeters, my mean is 237, my standard deviation is 54. My D at 20 millimeters, my mean is 197, my standard deviation is 59. And so for subject number 5, I plotted the data onto my left, and on my right I plotted that same data into a graph so you can visualize it. And so for subject number 5, my D at 0 millimeters, my mean is 250, my standard deviation is 42. My D at 5 millimeters, my mean is 225, my standard deviation is 46. And D at 10 millimeters, my mean is 172, my standard deviation is 20. And my D at 20 millimeters, my mean is 174, my standard deviation is 36. And so I calculated my estimated relative accuracy for my subject and my D value by using the following equation: 1 minus the standard deviation divided by mean. So for subject number 1, my D at 0 millimeters is 0.802. My D at 5 millimeters is 0.894, and for D at 10 millimeters is 0.783, and my D at 20 millimeters is 0.726. And this is my estimated relative accuracy. And for subject number 2, my D at 0 millimeters is 0.787. Subject number 2 at 5 millimeters is 0.731. Subject number 2 at 10 millimeters is 0.783. And subject number 2, my D at 20 millimeters is 0.707. And this is my estimated relative accuracy. For subject number 3, my D at 0 millimeters is 0.805. That's my estimated relative accuracy, ERA for short. Subject number 3, my D at 5 millimeters is 0.734. D at 10 millimeters is 0.761. My D at 20 millimeters is 0.870. My subject number 4, D at 0 millimeters is 0.758. D at 5 millimeters is 0.787. My D at 10 millimeters is 0.772. For my D at 20 millimeters is 0.700. And subject number 5, my D at 0 millimeters is 0.832. For my D at 5 millimeters, 0.795. My D at 10 millimeters, 0.883. And my D at 20 millimeters, 0.793. And this is my estimated relative accuracy for each subject and each D value. And I calculated my accuracy for each subject and each D value by using the following equation. I got the equals to the estimated relative accuracy times 100. So for subject number 1, my estimated relative accuracy at D at 0 millimeters is 80.2. D at 5 millimeters is 89.4. Estimated accuracy. D at 10 millimeters, estimated accuracy is 78.3, and D at 20 millimeters is 72.6 estimated accuracy. My D at 0 millimeters for subject number 2. My estimated accuracy 78.7. My D at 5 millimeters. My subject estimated accuracy is 73.1. My D at 10 millimeters. My estimated accuracy is 78.3. And my D at 20 millimeters. My estimated accuracy is 70.7. For subject number 3, my D at 0 millimeters, my estimated accuracy is 80.5. My D at 5 millimeters, my estimated accuracy is 73.4. My D at 10 millimeters, my estimated accuracy is 76.1. And my D at estimated accuracy is 20 millimeters is 87. And for subject number 4, my D at 0 millimeters, my estimated accuracy is 75.8. My D at 5 millimeters is 78.7 estimated accuracy. My D at 10 millimeters, my estimated accuracy is 77.2. My D at 20 millimeters, my estimated accuracy is 70. Subject number 5, my D at 0 millimeters, my estimated accuracy is 83.2. My D at 5 millimeters, my estimated accuracy is 79.5. My D at 10 millimeters, my estimated accuracy is 88.3. And my D at 20 millimeters, my estimated accuracy is 79.3. And so I'm gonna answer some questions I'm going to answer the questions 6 and 7. And so actually accuracy does depend on whether subject reaction time is long or short, because the accuracy depends on the subject reaction time, because that is where you get your data from. And in order to calculate your accuracy, and that's why it gets affected, because that's where you get your data. It depends on all your data. And so your accuracy though does not depend on your D value, because your D value only plays a small role in the accuracy. The D value is simply the means for you to get your data, and when you gather your data, you then simply input that data in order to calculate your accuracy. And so I'm going to answer for A to D. So if you're going up at a constant velocity of 5 meters per second, and the reaction meter will not be affected if the measurements were made in an elevator with constant velocity, because the gravity will still be the same at 9.8 seconds. It will not change your reading. It is the same as you were on the ground. The same goes for the constant velocity going down at 5 meters per second, because of the stated before is the same as if you were on the ground. For C, if you're going up at a constant acceleration of 5 meters per second, the reaction time will relatively be larger if you're going up at a constant acceleration of 5 meters per second, because the equation would not still apply, because gravity would then be 15 meters per second, not 9.8 meters per second. So if you're going to correct the reaction time, you will modify your equation where G is equal to 0.0015 millimeters per second. And if you're going down at a constant acceleration of 5 meters per second, in this case the reaction time will be relatively smaller. If you're going up at a constant acceleration of 5 meters per second, because as stated previously, the equation will still not apply, because the gravity would be 5 meters per second, not 9.8 meters per second. So if you're going to correct the reaction time, you will modify your equation where G is equal to 0.005 meters per second.